Hello, this is a video for compiler design, COMP442 and 6421. This is for week 8. In this video, I'm going to talk about bottom-up parsing. So it's going to be next week also is going to be another part of parsing, second part. So let's go to sharing the screen. So as you may have seen by now, and what was clear from the beginning of this course, this is a very much practically oriented course, and everything I've been talking up to now in the lectures was things that you have to do in the project. Okay. This is going to be these 2 lectures, which are the exception to this rule, for the simple reason that you cannot be talking about compiler design without talking about bottom-up parsing, because most of the industrial compilers are done using bottom-up parsing. So bottom-up parsing is the most used parsing method that you will ever see if you deal with compiler design in real life. So here I'm going to present in general what is called Lr parsing in terms of bottom-up parsing. There are some other methods. I'm not claiming that I'm presenting everything here. So I'm just presenting the most, I would say, prevalent methods which for bottom-up parsing, which are the Lr parsing methods. There are other methods. There are other methods, in fact, that are not Lr methods for bottom-up parsing, but I chose to concentrate more on this course in practical aspects of the implementation of the compiler rather than completeness of discussing all that there is to know about compiler organization or algorithms. So there are some of them that we don't cover in this course. I'm not claiming that this is complete. So here, let's go and talk about some concepts describing what is bottom-up parsing. Because you will see that even though this is parsing, of course, this is doing the same job as we have seen in essentially LL1 parsing that we've seen before and that you're using in the project. So it's still doing parsing. So many of the concepts are the same or resemble or have an equivalent between, of course, bottom-up and top-down parsing. But there are some specific concepts related to bottom-up parsing that you don't have in top-down parsing or LL1 parsing. So what is the difference between top-down and bottom-up parsing? So a top-down parser will construct a derivation from the root of the tree to the leaves of the parsed tree. Just bring up my pointer here. And so that's what we used, that's what we did in the methods that I've shown up to now, the parsing methods I've shown up to now. But the bottom-up parser, on the other hand, constructs the reverse derivation from the leaves up to the root of the tree. Okay. That's why I call it bottom-up parsing. The difference in terms of the power of the method, what's the percentage of grammars, you might say, that it's able to handle. Bottom-up parser can actually handle a much larger class of grammars. Okay. As we saw very clearly and somehow painfully in the project, if you want to implement LL1, if you want to implement top-down parsing, if you want to do predictive parsing, you have to have an LL1 grammar. So not many grammars are actually LL1 grammars, but there's ways you can actually remove ambiguities and left recursion to make a non-LL1 grammar an LL1 grammar. Fact of the matter is that if you want to implement your parser using a bottom-up method, it will actually be able to process many more grammars compared to top-down parsing or predictive parsing or LL1 parsing. Okay. So the in general, the bottom-up parsing methods are more inclusive in terms of how many grammars they can parse compared to top-down parsing. So most parser generators will use bottom-up methods. If you use a program, automatic program that will generate a parser, which you always end up doing when you are doing an industrial compiler, you don't do that by hand. You can actually implement a tool that will automatically, from the rules of the grammar, actually generate the table. Much like what we had, when I explained how to generate the LL1 table from the grammar. There's a procedure that you apply. You take the rules of your grammar. There are some heuristics that you apply that are going to transform your grammar into a table. The same thing goes with bottom-up parsing. You can take your grammar rules, and then you can actually apply some heuristics, which I will show today, and then transform this grammar into an Lr parsing table. And that's what, in fact, a parser generator is doing. It's automatically doing this translation of the grammar into a table. Then it provides you with a generic algorithm that can use this table, that can work with any table. So the fact of the matter also is that it requires much less grammar transformations compared to a top-down parser. Generally speaking, it requires no transformation at all. There is often some ambiguities, but they are much less prevalent than or problematic than when you are implementing a top-down parser, as we saw in summit number 2 in the project. So what other concepts? So the bottom-up parsing or Lr parsing family is often called shift-reduce parsers. Why? Because they are actually doing two operations. Depending on the situation, it will either do a shift operation or a reduce operation. Now, what is a shift operation? Shift operation will push the look-ahead symbol onto the stack and read another token. So you may recognize there the match function that we actually had in LL1 parsing. Essentially, you see a certain non-terminal that is incoming, and you recognize that it's a valid non-terminal. You consume this non-terminal and you push it onto the stack. Exactly the same concept we had in LL1 table-driven parsing, or the match function in the recursive descent predictive parser. So you see that it uses specific terms, but it's, of course, the concept, these are still parsing concepts. They are similar, but not exactly the same. For example, reduce is not exactly the same as what we used to have. What is reduce? Reduce matches a group of adjacent symbol beta on top of the stack with the right-hand side of a production, and then replaces this beta with the left-hand side of the production. Essentially, what reduce does is that it tries to see a certain right-hand, it tries to look up a certain right-hand side, a full right-hand side that is on top of the stack. If it sees a right-hand side on top of the stack, then it will actually remove this right-hand side from the top of the stack and replace it by the left-hand side that corresponds to this right-hand side. Okay? Essentially doing the application of a rule, but in reverse. Okay, so keep in mind that it's actually doing in reverse. So it's doing a bottom-up rather than a top-down. So something is doing reverse. That's what is happening. It has the symbols on top of the stack. It's trying to look for a sentential form that is corresponds to one of its right-hand sides and gonna replace it by the corresponding left-hand side. So reverse application of a rule. Then there's a restriction. You reduce only if beta is a handle. So handle is another concept of bottom-up parsing. Handle of a sentential form is a portion of this sentential form that matches the right-hand side of a production and whose reduction to the non-terminal on the left-hand side of this production represents one step along a reverse rightmost derivation. Essentially what it says is that you do this replacement only if this replacement represents a step toward a rightmost derivation or reverse rightmost derivation. There are different cases where you would actually see a right-hand side, but maybe this right-hand side is actually a subset of another right-hand side. So in this case, you would continue further and replace the bigger one. So not only you do reduce just blindly, you reduce only if it's the sentential form you found on top of the stack is a handle. So what does it mean, LL versus LR? So as we saw, LLK stands for scan left to right, because of course you're reading the program from left to right, and then you compute a leftmost derivation. So if your derivation is going forward like this, then you actually take always the leftmost symbol that has not been transformed into a sentence, basically a part of the sentential form that still contains non-terminal symbols. So you take the leftmost non-terminal symbol and you eventually want to replace it into a terminal symbol, and then you proceed your way through this list here until you come to the end of the list, at which point at the end what you have is actually a sentence. So if you have E that can be transformed into this sentence, which was your input sentence, then you have proven somehow that this grammar can generate this sentence, which is your program. So you have proven that this program is a valid program according to the grammar. Now, the Lr parsing is actually doing the same process, but somehow in reverse order. In the in the sense that it actually starts with the sentence. And then it wants to take this sentence and then transform it into the starting symbol. So it will start from left to right always, because we're reading the program from left to right. And then it's going to compute a rightmost derivation. Why is it rightmost? Because if you read in this order, in the forward order, the derivation starts here and then goes here. It's just that here I have expressed it in reverse order. So if you would present it in the correct order, you would start here, and then you would realize that you're actually transforming the symbols. The first symbols you are transforming are always those that are on the right. Okay, so that's why it's a rightmost derivation if you see it in a forward way. But if you see it in the backward way or inverse way, then of course you're still processing the symbols from left to right. Okay. Still, this is a rightmost derivation, because if you see it in forward way, then you are always transforming the rightmost symbol. Okay. So eventually what you're going to do is you're going to transform the terminal symbols into non-terminal symbols until you will eventually, and you will resolve them from left to right until eventually, hopefully, you will come to your starting symbol. Okay. So you see that you actually are building, in this case, exactly the same derivation as the leftmost derivation. So you see that for any program, there might be more than one derivation that is actually possible. It's not to say that it's ambiguous, it's just that there might be a different order in which you apply the different rules, depending on where you start, leftmost or rightmost. Now let's do a little bit of history. So what is Lr Parsers? How does it start? It actually starts with Donald Knuth, who actually invented this LRK, here we're going to be using LR1, but LRK in general, well, K, what does the K mean? It means how many tokens, or how many tokens do you need in order to proceed with the parse. In general, what you want to have is a parsing method that only needs to have the one next token, okay? Or else you may have to do backtracking. We already saw that you don't want to have backtracking because it's inefficient. So the LRK method was invented by Donald Knuth in 1965. So you see that most of these methods that we are still using nowadays were all invented in these early days where the programming languages were themselves invented. Okay. So that's back in the day, well, Lisp and Algol and all these ancestors of all the languages that we know nowadays were actually invented, and Fortran and so on. So what is characteristics of the Lr parser? Lr parsers can be constructed to recognize virtually all programming language constructs for which a context-free grammar can be written. Now, that's not to say that Lr parsers can deal with any grammar. Here, what I'm basically saying is that if you have the grammar of a programming language, which is a very restricted set of all the possible kinds of grammars, so if you write down the grammar of a programming language, extremely likely that you can actually resolve the parsing of this language using an Lr parser. Okay. There are many grammars that you can imagine that are not Lr grammars, but you would I would defy you to actually write the grammar of a programming language which cannot be parsed using an Lr method. Okay. So this is where a pure study of pure mathematical analysis of what are different grammars and how are all the methods able to process each grammar that is possible to imagine. Okay. Here we're dealing with grammars that represent programming languages, which is a very restricted set of among the set of all the possible grammars. Okay. So if you're talking about the set of grammars for a programming language, Lr parsing is extremely improbable that you cannot process it using a Lr parser. The Lr method is the most general non-backtracking shift-reduce parsing method known. Yet it can be implemented as efficiently as other shift-reduce methods. So there are different kinds of Lr parsers, which are all under the family of Lr method of parsing, as we will see next week. So next week, I'm going to present some variations of Lr methods. So the Lr method in general, it is the most powerful known parsing method that can parse as many languages as possible. There are some variations, but in general, that's what it is. That's not to say that there's no new things that are discovered using in the area of parser methods, parsing methods. But it just happens that they just happen to be variations or optimizations of what is already existing. A class of grammars that can be parsed using Lr methods is a proper superset of the class of grammars that can be parsed using LL predictive parsers or LL1 parsers. So you will not find a grammar that can be parsed using LL parsing or LL1 parsing that cannot be parsed using Lr parsing. An Lr parser can detect a syntactical error as soon as it's possible to do so on a left to right scan of the input. As we hinted at when we talked about error recovery in LL parsing, there is one of the problems with LL parsing is sometimes it will detect an error after it will realize that something was an error after it would actually been passed the token at which the error is happening. Okay. which is of course creating problems on reporting errors and also from recovering from errors. Lr Parser is very good at this, being very accurate at reporting errors and also a bit more effective at recovering from errors. Okay. Also, maybe I'm going to add something about Donald Knuth. For those of you who know the TeX typesetting system, actually Donald Knuth is the person who actually wrote the TeX typesetting system, which eventually was transformed into LaTeX that you may want to know. You may know more nowadays. But the fascinating thing about this history of Donald Knuth and the TeX system is that he was actually writing a new version of his very famous books, The Art of Programming, Computer Programming. And then he was faced with the fact that he was using this at this day, it was an antiquated system that was used for the typesetting of his book. And then he realized that this system has been changed, and then he would have had to use a new system, which he was actually finding was not to his liking. It was not producing the results that he was expecting. So he basically said, well, I'm going to write my own typesetting system. So he's actually invented the language TeX and then wrote a compiler for it. And then he actually generated some code in Metafont and so on. So that essentially he was working on a compiler design problem to generate text for his own book. So that's the kind of person Donald Knuth is. So just have a need here for my book to be published. I'm just going to write an entirely new new typesetting system. And then fast forward some decades after, hundreds of thousands of people worldwide are actually using the system. It's actually the standard for typesetting systems. So that's the kind of thing you can achieve when you are at the right place at the right moment with the right mind, right? So what are the different kinds of Lr parsers? There are variations of Lr parsers. We will see that in more detail next week. There's first a SLR or simple Lr method. So that's one is the easiest. That's what we will see today. I'm going to start with this one. It's the easiest to implement, but it's the least powerful. And then it may produce parsing table for, may fail to produce parsing table for some grammars. The problem happens when SLR can fail, or when LR can fail, is when you have a conflict between a shift and a reduce action. In a certain circumstance, you make a decision as to whether you will make a shift or reduce. If you're in a certain circumstance where you can either do shift or reduce, or you have two options of doing two different reduce, then there's an ambiguity. Okay. So SLR is prone to more ambiguity. In the family of LR methods, SLR is the most prone to fail on ambiguities. Then there's a canonical LR or CLR. This one is the most powerful. It's very extremely general, so it will fail less often than SLR, but also it's most expensive method. What's mean by expensive is that it will generate many more states. So it's a state-based algorithm. So you have in your table, basically your table is a state transition table. If you have for the same grammar, you generate the table for SLR and you generate the table for CLR. The CLR table will contain many, many more states. Okay. The more your right-hand sides are long and the more you have rules, the more you have some kind of state explosion happening in the number of states that you have for this grammar. So CLR will generate many, many more states compared to SLR. So that's what the reason why there needed to be some compromise, because in the 1960s, as you may imagine, the computers did not have as much memory as we have now. So memory was a very important factor in success or applicability of a certain solution. So the more the languages were getting more complex, the grammars were getting more complex. And then if you would use the CLR method, the tables would become larger and larger and then would not fit in the computer's memory. Okay. So they had to find intermediate solutions between SLR and CLR. And one of the solutions was LALR, or look ahead LR. This one is basically in between CLR and SLR. The idea, as we will see next week, behind LALR is that it's actually trying to find, to reduce, it's basically the same thing as CLR, except that it will actually try to find states that are similar to one another, and will try to merge states that are similar to one another, thus reducing the number of states in the graph. Now, this is a depiction of what is an Lr parser. So Lr, well, as any parser, it will consume a stream of tokens. So that's one thing that this parsing algorithm is consuming or using. So that's basically your program here that comes inside of the parsing program. It is using a table. So you have, in this case, it's a state transition table. So there's two parts to this table. There's the action part and there's the go-to part, as we will see later in this video. So essentially your parsing algorithm sees a certain token in input, and then it will somehow look up into the table as to what is the next action to be taken. Either it's going to be a shift or a reduce action, depending on what's happening. Now, depending on what's happening also depends on what is also on top of the stack, because depending on what you have parsed in the past, let's say you were now in the middle of going forward in a certain right-hand side, then as you're going forward in a right-hand side, you will actually take the symbols that you go over as you parse, and you will actually take them and push them onto the stack. So the stack is there for the algorithm to actually remember what happened, what is it that it did in the recent past. For example, it was going forward in a certain right-hand side. And eventually, that's how the parser will be able to recognize that on top of the stack, there is a certain right-hand side, and it's going to remove this right-hand side from the stack and replace it by the corresponding left-hand side. Okay. So the parsing stack is somehow the memory of this parsing algorithm. So it uses both the notion of a state transition as well as the notion of stack or memory. So it's essentially a push-down automata kind of solution, right? So all Lr parsers are table-driven. So they are CLR, LALR, and SLR. All these three methods and some others are also using the same kind of table, where it's a state transition table, and you have an action part and a go-to part. Whereas in the action part, that's where you decide where you do shift or reduce. The go-to part, as we will see later, actually makes you somehow decide to which other state you go after you have applied a reduce operation, depending on where you were before you actually started going forward in this particular right-hand side. So all Lr parsers are table-driven, which is derived from a finite state automaton generated from the context-free grammar that represents the language. So you take your grammar, the rules of your grammar, you apply a set of heuristics, pretty much resembling somehow what we had in the generation of the LL1 table-driven parser, the table for the LL1 table-driven parser. You have the rules of your grammar, you have heuristics, and then you follow these heuristics. You look for certain patterns in your grammar, and then it tells you, some of the heuristics tell you to put some entries in the table and the appropriate places in the table. Similar kind of approach, but of course the heuristics are not the same. The same algorithm is used to parse independently of what is the Lr parsing method used. So this algorithm here is the same. So you don't have a different algorithm for CLR, LALR, or SLR. It's the same algorithm. The difference is what are the heuristics, or what is the method that you use to actually construct the table. So this is essentially using a push-down automata because it's using an automaton. So it's a state transition-driven procedure, but it also needs to use a stack in order to remember some information as to basically what path it took in this FSA, and that at some point in time, it's going to want to go back, basically to backtrack some of the state transitions that it made, and then start back and take another path, and so on and so forth. Okay. So it needs to remember what is the recent history of the path that it took as it went over this FSA, so that it can actually go back a few steps, then start back at a certain point before, and then go in another direction until it reaches the final state. So only the nature of the Lr method used to generate the table distinguishes the parsing method used. So the only difference is how you construct the table. The methods are extremely similar, but there are some variations as to what there's additional information that you can use in the generation of the table that is going to make some, how can I say, to make it more powerful and more use a better discriminates as you are generating the table. So that's to make the parsing method more powerful to accommodate more number of grammars. So all Lr methods use tables have two parts: the action part of the table, which dictates whether a shift or reduce action is needed. Then the go-to part dictates a state transition after you have applied a reduce operation. So here's the Lr parsing algorithm. So you will see that it actually, conceptually speaking, has a lot of resemblance between this and the LL1 parsing method. Of course, it's not the same. It's state-based and so on, but the underlying concepts, of course, these are parsing concepts. And this is also using a stack, so there's a resemblance from this part also. Though on the stack, you don't only, in this case, you don't only store symbols, you also store states. Okay, so that's one of the major differences. Remember, the LL1 table-driven parser was using a table, but it was not using states. It's not a state-based method. This one is a state-based method, state transition-based method. So first of all, this is a state transition diagram. So you should start at the starting state. What is the starting state? Of course, state number 0. So you start by pushing the state number 0, your starting state, on top of the stack. Then, as we had in the LL1 terminology, we assume that X is the top of the stack and A is the next token. Okay. Then you have this repeat forever loop here, which ends only if you hit either return true here or return false here. If you return false, of course, that means you have had a parsing error. That your parsing resulted in the conclusion is that you cannot parse this input stream. So you have three main things that can happen. So it's either if you go into the action part of the table over here. So this is the action part of my table. Let's just describe what the table is. So the table is, first of all, there's a row for each of the states of your FSA. Okay. We will figure out, I will explain later how you come up with the states. Okay. Here, just take for granted that we have this table. So for this particular grammar, there's 11 states. Then in the action part of the table, you have one column for every of your terminal symbols, much like you had in the LL1 parsing table. Except that in the LL1 parsing table, what you had here at each row was the non-terminal symbols. Here, it's the states of your FSA. Then in the go-to part of the table, again, for every state, you have some entries for each of the non-terminal symbols. You may have some entries that correspond to certain states. There are some entries, again, that don't have any, have some cells that don't have any entries. In this case, in this particular case, if you are using this parsing method and you are peeking into a table and you go into an empty cell in the go-to table, that means the go-to table was wrong. Okay, that doesn't mean that there was a parsing error. However, if you hit an empty cell here, that's a different matter, but it just cannot be that you would peek into an empty cell in the go-to table. Or if you do, that means your go-to table is wrong. Okay, so here you go in the action part of the table at coordinates XA. So X is the top of the stack, assuming that this is actually a state. And then you have a state, and then A is the next token. So let's say you were in state 0 and you see ID, then you see this here. S5 means this is a shift action. Okay. So when you peek in the table, you see an S, that's a shift action. If you see an R, that's a reduce action. If you have S, then the number that follows is actually a state number. So essentially that is a state transition. So you're in state 0, you see an ID, you transition to the state number 5. So you have essentially went over the ID that you saw in input and you actually go to state number 5. We will see later, I'll give you the FSA representation of this later on in the video. So if you have this, and then you find, for example, shift 5 or S5, then you actually push your A. So you went over this token A here, you take it from the input tokens and you push it on the stack to somehow remember you've successfully parsed this token. So you see that right away, you're going forward into a right-hand side. And as you're going forward, you actually push this piece of the right-hand side onto the stack. Then you would push this S prime onto the stack. Okay. So you see that your stack is actually alternating between symbol and state. It's always symbol, state, symbol, state, symbol, state. As opposed to our LL1 parser, which had only symbols on top of the stack. Then after you've done that, then you go to the next token. Okay. So this is what happens when you have a shift action. You take this token, you push it onto the stack, you push the new state that corresponds to the S action you found in the table onto the stack, and then you consume this token. You go to the next token. If that's not the case, then that must be that you have a reduce action. Here, note that this is not dealing with errors. We will see that what happens if you have errors next week or in the next video. So if it's not the case here, then if you go in the table and you see a reduce or R action, so if you see, for example, in state 2, you see plus and you see R2, then what R2 means is that you are, so this is my rules here. So this is 1, 2, 3, 4, 5, 6. So the R4, for example, is saying reduce 4. So reduce 4 would actually mean that I know I have an F on top of the stack and I want to replace this F by T. Okay. So you see I'm applying the rules in reverse order. I'm trying to find my right-hand sides on top of the stack. Then when I find it, this is going to be a handle, and I'm going to remove this handle from the stack, and then I'm going to replace it by the left-hand side that corresponds to this right-hand side in the particular rule I have identified. And that's what my table is telling me. What reduce I should apply at this particular point in time. So how do you do a reduce? First, you have to pop from the stack. So you should remove from the top of the stack the right-hand side that you have just identified. Just happens, as I said before, that on top of in your stack, you always have alternating state symbol. So if you have a right-hand side of, let's say, length 3 on top of the stack, you have to pop 6 things from the stack. So that's why you pop twice the length of your right-hand side from the stack in order to remove also the states that came with every symbol that you have pushed onto the stack when you did shift actions. So you pop your right-hand side from the stack, then you remember what is the state that is under this right-hand side onto the stack. Then you will actually replace the beta, the right-hand side, by A onto the stack. Then you actually go into the go-to table, and then you peek into the table at coordinates S prime, which is the state that was on top of the stack below your right-hand side. And then you peek into the table at this state that was below your right-hand side onto the stack in the go-to table at this state, and then non-terminal A that you just pushed onto the stack. This will tell you what is the transition state, which state you will transition after having applied this reduce operation. Okay. You see that you have action and go to. So if you do a shift, you go to the action part. If you go to action part, you find shift and you do this operation. If you go to action part, you do and you find reduce, you do this operation, then you go to the go-to part. So the go-to part of the table is used only when you apply a reduce operation. Then you have successfully applied this rule here in reverse order in the derivation. Then the only other thing that can happen is that if you see accept in the table. So accept actually means that you have successfully parsed the program. There should be only one accept in your table. In this case, it's from state 1. So if you're in state 1 and you see the end of the program, this is the accept action. So if you keep peek in the table and you see accept, you basically return true. Okay. So this is how this algorithm is working. Now let's actually use it in an example. Now, I have to say, normally I have, I'm not stuck with this only this media here. Normally I have my blackboard, I write on the blackboard and I have 2 different displays and so on. So I feel a little bit claustrophobic here in my presentation, but hopefully it's going to go well. So how does it go? So I first push 0, my state 0 on top of the stack. Then I go into this algorithm, which tells me I should look into the action part at coordinates top of stack and next token. So top of stack is 0, next token is ID. So 0 ID tells me shift 5. Now, what is shift 5? Shift 5 is you push A. So you push this token that I had in input, which was my ID. So the token I had in input here was ID. So I take this ID here and I push it on top of the stack. Then I actually take the S prime, which is a state number, and I push it onto the stack. So I take the 5, because I had shift 5 from the action table, and I push 5 here. So now I have 0 ID 5, and then I consume this token, so now I'm at plus. And I do another iteration, 5 plus. What is 5 plus telling me? 5 plus is telling me reduce 6. So what I'm going to do here, and I'm going to transform this ID I just parsed, and then I'm going to transform it into an F. So I have to remove this ID here, but because it came with its state here, within the state here, I have to, if I want to remove the ID, I have to remove 2 things from the stack. So the length of this is 1, so times 2 is 2, so I pop twice from the stack. Then, okay, so let's go to the algorithm. I'm going to do this for the first ones, and then I'm not going to come back to the algorithm after. So I pop my 2 things from the stack here. Then I remember, after I popped my right-hand side from the stack, I remember what was the state on top of the stack. Then I push A onto the stack. Then I go into the table at coordinates S prime A. So essentially what's happening here is that I pop the 5 and the ID. Then I'm left with 0 on top of the stack. Then I push F. Then I go in the go to table at coordinates 0, F. If I go in the table, 0, F tells me 3. So what this is telling me is that if I'm in state, if I just apply this reduce, if I applied a reduce operation and I find myself in state 0, and what I just did is to reduce an F, then I should go to state number 3. Okay. So 0, F, 3. Then I go 3 plus, another iteration. 3 plus is reduce 4. Reduce 4 is transform the F I have on top of the stack into a T. So I remove the F on top of the stack, so remove 3 and F, and then I have 0 on top of the stack, and then I push T, because I was transforming this F here, the right-hand side, into a T. Then I go in my go-to table 0T, and then I will find 0T. I find 2, which I push on top of the stack. Then another iteration, 2 plus. 2 plus is reduce 2. Reduce 2 says transform this T into an E. So I pop the 2 and the T from the stack to remove this right-hand side from the stack. Then I have myself again at state 0, and then I push E, which is the left-hand side. Then if I go in the table at coordinates 0E, 0E, I find 1. So I push 1. Then other iteration, 1 plus. 1 plus is shift 6. So shift 6. You take this plus here and you push it onto the stack, and then it's a shift 6 operation. So I push 6 onto the stack. Then 6 ID. If I go in the table, I'll find shift 5. So then I take my token here and I push it here, and then I push the state number here onto the stack. Then I go in the table again 5 times. 5 times I will find reduce using f gives ID. So essentially I'm going to take this ID here and replace it by f. So I remove the 5, remove the ID. I'm now in state 6. I push the F. I go into my go-to table 6F. I will find 3, which I push onto the stack. Then I go in the table again, other iteration, 3 star. I will find reduce T gives F. So I'm going to remove this F here from the stack, the right-hand side, and then I'm going to push T. And I'm going to go into the go-to table 6T, and I will find 9, which I push onto the stack. Then I have 9 times or 9 star. If I go in the table, I will find shift 7. Shift action, I take the next token, I push it onto the stack, and I take this state here and I push it here. Then 7 ID. 7 ID, I will find shift 5. So again, I take ID, push it, and I take 5 and push it. Then I go in the table $5. This is where it concludes, starts concluding. Then $5 tells me apply reduce, giving using this rule here. So I want to take my right-hand side, remove from the stack, and replace it by F. So I take my ID and its corresponding state, remove it from the stack, replace it by F. I go in the go-to table 7F, I will find state number 10, which I push onto the stack. Then I'm going to go in the table another iteration, $10 tells me T gives T times F. So you see here that I have on top of my stack T times F. So I'm going to remove this T times F, essentially twice the length of this. I'm going to pop 6 times from the stack. So I'm going to pop 1, 2, 3, 4, 5, 6 things from the stack, which is my T times F. And then I'm going to replace it by T. So now I had 6T. Then I go in my go-to table, 6T, I will find 9, which I push here. So you see here, that's what it tells me is that as I was starting to actually parse the T times F right-hand side, before I started going my way into this right-hand side, I was in state 6. And then this table is telling me that if I'm in state 6 and I was parsing a T, then I should go to state 9. That's basically what it tells me. Then, again, continue, $9, I will find reduce using E gives E plus T. So I pop 6 things from the stack. I pop my E plus T from the stack. 1, 2, 3, 4, 5, 6 from the stack. And then I replace these E plus T by E. Go in my go-to table, 0E, I find the state number 1. Then another iteration, I go $1, I find accept. Thus, I have done a proof that this input token stream is a valid stream of tokens for this program, for this grammar. Okay. Now this is taken for granted that we have the table. Okay. I just wanted to show you how it works before I show you the real magic of this whole thing, which is happening when you actually construct the table, right? So let's go and see how it works. So what is this table? It's essentially it's a state transition table. It's a representation. The table is a representation of the states of a DFA that you are constructing. So you are essentially transforming the rules of your grammar into a DFA. So what are the states? Because this is basically you're transforming a grammar, the right-hand sides of a grammar into using the right-hand sides and left-hand sides of a grammar to transform it into a set of states. So what are the states? States, they represent what has been parsed in the recent past on the way to recognize a handle. So as you're making your way forward in a handle, every step of the way, you go to a different state. Okay? Depending what are the choices that you have to make, depending on the context that you are and the choice that you make, you go on a different branch in this DFA. That's why you need both to remember where you are right now, what's your context, so that depending on what state you are, depending on the context you are, then you'll make a different decision. And depending also what's the next token and input, you will go to a different branch in your DFA. The states will also control how the DFA will respond to the next token and input. Of course, you will make your choices, yes, depending on what right-hand side you're currently going forward in, but also, and mostly, also take into account what is your next token and input, because you will proceed forward only if you know, the next token and input is valid. And that's this next token that very often will tell you in what direction to go in the DFA. And finally, a stack is used to keep track of the yet unresolved part of the path taken by the parse. Okay, so you're going into this DFA in two different states. You have to remember what is the path that you took in the recent past, so that if you are starting going in a certain path, which is going forward in a certain right-hand side, and then you find yourself in a certain state at the end of this right-hand side, then you know you have to somehow undo or remove this right-hand side from the stack. So that means you have to somehow undo this track until you come to the point where you started going forward in this particular right-hand side. Okay, so that's why you need to have the stack, so that you remember what is the path that you took up to now, so that you can actually revert back to where you were before you started going forward in a particular right-hand side. So the goal of this is actually to reduce handle, as we saw in the example here. It is you know, the stack is growing bigger and bigger, but eventually it is resolving itself when it finds some right-hand sides, in which case the stack is reducing. And then eventually what you want to have is to come to the state that has the accept action, and that you will see the end of the program as your next token. So if you come, of course, if you come at the end of the parse, if you come to, you come to the end of the program and you still have things on top of your stack, that's going to be a parsing error. And then you're going to have a skip error function that is going to want to either pop from the stack or consume tokens, similarly to what we had in the skip error function for the top-down parsing. Conceptually similar, but of course different, because here we're talking about states and so on. So next very important concept, so to keep track of how far we've gotten through the growth of a handle as you're going forward in a right-hand side, you are going forward in the identification of a handle that you're going to reduce. So the way you use to actually figuratively represent how far you are in a handle is to use what is called items. Items is the main concept in transforming the grammar into a table. So let's look as to what is items. So what an item is, like essentially a production with a place marker that is inserted somewhere in its right-hand side. And this place marker is actually indicating where you are currently in the identification of this handle. So if you have this rule E gives E plus T, if you have E gives dot E plus T, that means you are here in the processing at the beginning of the processing of this handle. However, if you have E gives E plus dot T, that means you already passed the E successfully and already passed the plus successfully. Now you are here and you are expecting a T to be successfully identified in the parsing process. So the symbols on the left of the dot are already on the stack. So if you are in this state here, that means the E and the plus are already on top of the stack. So the goal is to come to the end here and then to actually remove from the stack the E plus T and then replace it by E. Okay, so the goal is to, of course, have the dot at the end of the right-hand side and identifying it as a handle and then apply a reduce operation. So all this idea here is to keep track of where you are in the processing of a particular right-hand side. So how does this relate to shift and reduce? So shift action taken by the parser represents the moving of the dot within a right-hand side, transitioning to a new state in the DFA. So in your DFA, the transitions between the states are the consuming or having successfully parse a certain symbol, either a terminal symbol or a non-terminal symbol. So the effect of going from here to here would be that you have successfully parsed an E. Okay. Here you would, if you go from here to here, you would have successfully parsed a plus. If you go from here to here, you would have successfully parsed a T. So you see that the transitions between states are about having successfully parsed a particular symbol, non-terminal or terminal. I'm going to show you the graph just so that you have a glimpse of what I mean here. So that would be, for example, you're in state 0. If you're in state 0 and you successfully parse an E, you go to state 1. If you're in state 0, you successfully parse an ID, and you go to state 5. If you're in state 0, you parse a T, you go to state 2. State 0, you parse a F, you go to state 3. Okay. So you see that the transitions are either parsing a terminal symbol or a non-terminal symbol. And this is happening as you are literally going forward in a certain right-hand side by going to another item whose dot is one item, one symbol forward in this right-hand side. The shift action is in fact moving the dot further to the right on the right-hand side. What is a reduce action? A reduce action is taken by the parser, represents the inverse application of a grammar rule once we have come to the end of its right-hand side. So what you want is to have the dot at the end here, at which point you will remove this right-hand side from the stack and replace it by E. Okay, so you will apply this rule in inverse application. You will do an inverse application of this rule. In the top-down parsing, we were actually transforming an E into E plus T. Here, we're taking an E plus T and transforming it into an E. So you see that it's going in inverse direction. So once a handle has been identified, a handle is an item, a completed item. The elements of the right-hand side are removed from the stack and replaced by the left-hand side symbol. Then we jump to the state that corresponds to the next handle to be parsed, as indicated in the go-to part of the table, as I explained earlier when I basically gave you the parsing example. Now, there are different kinds of items. that have a specific name because if they have a specific function. An initial item is an item that starts with dot. So that's where you are literally at the beginning of the recognition of a handle. That kind of item is called an initial item. Then you have the completed item, where the completed item is one whose the dot is at the end here. So that's the goal we want to have. That's one of the main goals we want to have in this parsing procedure. Find completed item. That will tell us that we have to apply a reduce operation. Completed item, the item ends with a dot. These are candidates for reduction. So when we have a completed item, the handle has been recognized, and we can reduce this handle to its corresponding left-hand side non-terminal, applying the rule in reverse order. So moving the dot further to the right in the right-hand side actually corresponds to a state transition in the DFA. Now, how do we generate these states? So of course, we're going to start as state 0. So state 0 is the beginning of the parse. So essentially, we are starting at state 0 with the starting rule, the rule that defines the starting symbol. Then what we're going to do is we're going to compute what is called the closure of this particular rule. Now, the closure is, closure is all different possible intermediate expansions using the grammar rules. Okay, so for example, okay, I'm going to show in the example going forward in the following slide. So I'm just going to explain the concepts, and then we're going to see what they mean with the example. So you're basically going to, at a certain state, you're going to have a certain symbol that corresponds to the state, or a certain number of symbols that you went through in the recent past. And then the next thing is going to happen is that you're going to have some items. And then after the dot, there's going to be other symbols. And then depending on what symbol that you will go after, this will make you branch to a different state. So that's how you identify what are the different states. Okay. At any state, there might be actually, you will eventually find the closure of the rules that correspond to the state, the initial rules that correspond to the state. Then you will come with a set of items. And then you're going to determine what are all the symbols that are after the dot in all your set of items for this state. And then you're going to for each of the different symbols that you have in your after the dot in all your items, this will lead you to have a different branching out to different other states. So this essentially, you start with the rule that defines the starting symbol. You compute the closure of it. Then you will come with a set of items that can be expanded from the starting state, the starting symbol. And then you're going to branch to other states. And then the subset of items that you're going to use to branch to another state are going to become the starting items set for each of these other states. Then you will apply the closure on each of these, which will going to make you branch to other states. Eventually, some states are going to branch to other pre-existing states, and you basically repeat that until you don't have any more expansion to do, and that's where it stops. So you basically generate item sets. So if you look at the graph, the DFA that corresponds to the resulting DFA, you see that for state 0, I have a set of items. For state 1, I have a set of items. State 6, a set of items. So the trick is to find what are these items that correspond to every state. Just to explain a little bit further, maybe to make it easier to see when we're going to see the procedure to create this item sets. For example, if I'm in state 0, this is my set of items, which I will explain now a little bit later how we generate the set of items. So this is my set of items for this state 0. After the dot, I have either E or T or F or open parentheses or ID. Each of these are actually a transition to another state. If I'm in state 0 and I see E, I actually go to state 1, and this 2 here, I put the dot after the E here, and that becomes my starting items for state number 1. So in state 0, parse an E, go to state 1. If I'm in state 0, I parse a T, then I go to state 3. If I'm in state 0, I parse a F, parse a T, go to state 2. If I parse an F, I go to state 3. If I parse open parenthesis, I go to state 4. If I parse ID, I go to state 5. Okay. So this is how you determine what are the transitions between your states. Now the trick is, how do you determine what are your item sets? So after you've determined it for the state number 0, for each group of items with the same symbol to the right of the dot in the item set, we apply a transition to another state, as I just explained using the graph, the DFA. So essentially here, you're moving the dot one step further in the particular items that you have identified. If the state is a new state, meaning that the integral form to the left of the dot has not been encountered yet, then we compute its closure and further transitions. And then you repeat this until you don't have any more expansion to new things having been recognized, new sets of things having been recognized, or new sequence of symbols having been recognized. Okay, so here, two important concepts is the closure and the go-to. So the closure is what you use to actually determine what is the item set of a state, whereas the go-to is what you determine, what you use to determine what is the meaning of a transition between a state to a state to another. So in order to create a state, we identify the starting item set for this state and then compute the closure of this item set. So every time you start on a new state, you will have a starting item set. The starting item set for state 0 is the rule that defines the starting symbol. Then, okay, let's go back here. So the state 0, you start with the rule that defines the starting symbol. So S gives E. Then, for example, for state 1 is the state, when you are in state 0, if you go past the E in your items, then you go to state 1, and then the starting item set for state 1 is the set of items in state 0, all the items in state 0 which have an E after the dot. So I take both of these here, which are the only ones that have E after the dot, and they become the starting item set for state number 1. And I do the same for if I go past a T here, there's 2 of them. So if I go past a T, I go to state number 2, and then these 2 rules become the starting item sets, the starting item set for my state number 2. And then if I go past an F, there's only 1 rule. So this rule after the dot is moved after the F, that becomes my starting item set, singleton in this case, for my state number 3. Same thing for here. F gives dot open parenthesis, I parse the open parenthesis, then this item becomes my starting item for state number 4. Then I will apply the closure of each of these, which will make me create the total item set for each of these states that I have transitioned into. So what is closure? So it's always closure of an item set. Okay. So first of all, closure of an item is the item itself. Okay. So that's the fixed point of this iterative or procedure. Okay, if so let's define what is the closure of an item set. So the item set closure is defined on an item set. First of all, the closure of an item is the item itself. Second, if you have an item that has a dot inside of the right-hand side here, and that is followed by a non-terminal B, then I look into my grammar and I find all the rules that may actually expand this B into another sentential form. For example, I might have B gives gamma, as that being a prediction in my grammar. So essentially here, that means this B here can be transformed into a gamma. So that would mean if I go here and I go, I have basically a choice. If I have B after the dot, then if there are many roles for which a B can be defined by, then I would have different options by which I would go. And then I would basically, if I have a rule B gives gamma, then if I go past the B, then I would actually go into the identifying the right-hand side of this B. So I'm going in this path. If I'm taking another rule defining B, then I would be taking another path. Okay. So here, if I have this item here, which B follows the dot, then I have a rule B gives gamma, then I add to my item set for this state, B gives dot gamma. Okay, basically saying that I can, if I have a B after the dot, it can be the start of this gamma here. This B here can be the start of this gamma here if I replace the B by gamma, right? Then you essentially repeat this until you find no more items. Okay, so we will see that by examples as we go. So once you come up to a fixed point where you don't find any more items using by computing the closure, then you have identified what is the item set for this particular state. Then the corresponding, so this is how to define what is a state, essentially. How do you define what is a transition? Okay, transition is defined by the goto operation. So the goto, so essentially is defining a transition between a state to another. So it's goto between an item set and a symbol, because we already defined that the transition that are the transitions, how do you define a transition is you are in a state and you see a certain symbol. You basically go over a certain symbol, either terminal or non-terminal. So it's go to item set and symbol that defines what is a transition or a go-to operation. So essentially, a go-to of a item set I and a grammar symbol X is the closure of the set of items after you pass the dot after the X inside of your current item set, where this item is in your current item set. So if you have this currently in your item set in the current state, and then you make a transition to go to operation using X, then you will find yourself having in the item set of the new state, you will find yourself having this item as a starting item of the new state in which you just transitioned. So let's see an example. So let's start with state 0. So first of all, well, how do we define the states? We define them by what is it that we have parsed in the recent past. So if we start the parsing, we did not parse anything. So that's essentially this V notation here is what is it that we've parsed in the recent past. So V of nothing is essentially V of epsilon. So if I'm in state 0, by definition, I did not parse anything in the past. So state 0 is V of epsilon. So I have my starting rule. Well, that's one thing I did not define here is my starting rule here. So my starting symbol is S, and then S gives E, which is my expression. Okay. So this rule that defines my starting symbol becomes my starting item. Now I compute the closure of this starting item. Closure of S gives dot E. How do I do that? Essentially, I have here E after the dot. So what is it that this E can be? This E actually can be an E plus T, or this E can be a T. So I can actually, if I'm starting to parse an E, it can be this E here, which means it's the start of E plus T, or it's this E here, in which case it's the start of T, right? Now I have added these two items in my item set. Now it can actually be that I can be in the start of a T. Here I have start of E, I already computed that. Now it can be that I'm starting, the next thing I will do is a T. If the next thing I will do is a T, then T can be either T times F or T can be F. So it can be the start of T times F or the start of F. Now, as here I have F after the dot, then F can actually be E between parentheses or ID. So when I start doing this F here, can be actually the start of E between parentheses or the start of ID, right? Then I have no more items to add, because even these that I have added here, for example, this beginning of T here, would still be leading to the same items being added. Okay, so yes, it would add items, but it would not add new items that are not already there, right? So this is my set of items for my state 0. So if we go in the graph here, then we see this is my state 0 here. This is my set of items. Then what can happen if I have this state, this set of items? So, oops, sorry. If I have this set of items. So either I can move the dot after an E with either of these two here, or I can move the dot after a T with either of these two here, or move the dot after an F, or move the dot after open parentheses, or move the dot after ID. So each of these are actually leading me to a new state. So I have, and this graph, you're in state 0, it's either you move the dot after the E, which leads you here, move the dot after the T, leads you here, move the dot after F, which leads you here, move the dot after parentheses, leads you here, move the dot after ID, leads you here, right? So then if I go to after the E, two items can be used to do the moving the dot after the E. So these two items become the starting items of my state number 1. So state number 1 is the set of items in my state 0, which have E after the dot. So, and then according to my definition of goto, I actually take these two items and I move the dot after the E. That becomes my state 1, which is V of E. Because I was in V of epsilon, I moved the dot after E. So I've now, in the recent past, parsed an E. So V of E. So V of E is set of items, starting items is these with the dot move after the E. Then I would compute the closure of this. But as you see, closure is only expanding if there are some items that have non-terminal symbols after the dot. Here, I don't have any non-terminal symbols after the dot in any of my items. So the closure is actually the set of items, the initial set of items. Sorry. So that's the two. That's the end of my state number 1. Now you see that the only thing that can happen in state number 1 is that I would move the plus, the dot after the plus, which leads me to another state. Now I go back to state number 0. So basically here I'm taking care of every of my transitions that I have found. And I create new state, compute the closure. I'm going to find a new item set. And I'm going to find new transitions and create new states. And I will basically create transitions and new states until I have no more expansion to do or no more new transitions that I found. Okay. It doesn't matter which ones you resolve in what order. Okay. So in my proceedings, in the way I proceed, I actually go back to my state 0. Then my state number 2 here is moving the dot after the T. So I take these two items here. They become my starting items in state number 2, which is V of T. So V of epsilon plus parsing a T is V of T. So then I move the dot after the T's. And then I compute the closure. There's no non-terminal symbol after the dot in any of my items. The closure is the same as the set of initial items. And then what are the transitions from that? I can only transition from state 2 using by going over the star, right? Which would lead me to V of T star. Here, state 7 is V of T star. State 1 was V of E, state 2 was V of T, state 3 was V of F, state 4 was V of open parenthesis, state 5 was V of ID. In state 1, as I went from the dot from here to here, I go V of E plus. So state 6 is V of E plus, right? Then next state I didn't resolve yet is this one here. I identify here a transition to a new state whereby I'm going to transition using this F here. So I have state 3, which is V of epsilon plus F. So V of F. Move the dot after the F. So I have T gives F dot. The closure does not generate anything. So it's basically stops there. You see, this is a special case here where you have a state which does not lead to other states. The only thing that happens in this particular state, you have identified a handle. So next, the unresolved state is state 4 here. So state 4 is moving the dot after the closed parenthesis after V of nothing, which is V of open parenthesis. So I take this starting item, move the dot after here. Here I find myself in this interesting situation where I basically start all over again because I see an E after the dot. So what this E can be, it can be either E plus T or it can be T. Because it can be T times F, or it can be F. Because it can be F, it can be again E between parentheses or ID. Okay. So this is all my closure for this state number 4. Now this leads me again to many different transitions, either V of open parenthesis E or V of T. So you see here that this is leading me to V of T. Why is it not V of open parenthesis T? Because this one here was actually grouped with this one because they had both the same E after the dot, and this one was a starting item of V of open parenthesis. So this one is actually V of open parenthesis E also because it was grouped with this one. Whereas this one here is not going forward after any parenthesis, it's just T by itself. So this is V of T, which I already identified was state number 2. So you see here, I'm actually going to a state that I've potentially already processed. So this is how this is eventually going to end, because I'm going to identify new item sets, which will already have been computed. Then here I have moved the dot after the F, that's V of F, that's state 3, I've already identified that. V of open parenthesis, state 4, same state as this one here. V of ID is state number 5. So that's it for my state number 4. And then state number 5 is V of ID. So V of ID, so there's nothing, no closure here because I don't have any item that has a terminal symbol after the dot. So it's very simple one here. Then state number 6 is this item here, whereby I'm moving the dot after the T here. So that's V of E plus. So that's V of E plus. The dot has been moved after the plus. So I have T after here. So I compute the closure because this T can be T times F or it can be F. And because it can be F, can also be E between parentheses or ID. So that's it for my closure. Then these two items have a T after the dot. So they are both the starting items of state number 9, which is V of E plus T. And this one is grouped with this one here. That's why this one is going to the same state. As this one here was not grouped with any of the starting items, it's T times F. So this goes to state number 3. V of open parenthesis is state number 4. V of ID is state number 5. Then my state 7 was identified here. So that's V of T star. Take the starting item of my state number 7 is T gives T star dot F. F gives T, should be T. T gives T star F, star dot F. Then I compute the closure. This F can be E between parentheses or can be ID. Then I can have a transition if I have F here. You see that this F here is not grouped with any of these here. So that's essentially V of T times F, state number 10. Then I can go V of open parenthesis, state 4, V of ID, state 5. Again, I repeat, these ones are not, for example, V of T open parenthesis star, because these are not grouped with any of those of the starting items. So then my state number 8 was found here. What is state number 8 is V of open parenthesis E. So these two items become the starting items of my state 8 after the dot has been moved after the E in both of these items. So that's f of open parenthesis e dot close parenthesis. Yes, e gives e dot plus t. Then you see that both of these items, they don't have non-terminal after the dot. So there's no closure, there's no addition of any other items by the closure operation. So in this, after I move the dot after the close parenthesis here, that would be v of e between parentheses. If I move the dot after the plus here, that's v of e plus, which is state number 6. If I move, no, I'm sorry. I was continuing on the list here, but that's the end of the list of items for state number 8. And my state number 9 was identified here. So that's v of e plus t. So I actually take these two items here, which have t after the dot, move them to my state number 9. They become the starting items of state number 9 after the dot has been moved after the t. So state number 9 is e gives e plus t prime dot, and t gives t dot times f. There's no items with a non-terminal symbol after the dot, so the closure does not add new items. So that's the final set of items for this state. Then my state number 10 here is the v of t times f. So I take this item here and then push it into my state number 10. Then I moved the dot after the f. So that's my starting item set for my state number 10. Of course, this does not, the closure does not add anything. So that's my final set of items for this state. Then my final state, which is not resolved yet, is state number 11, whereby I moved the dot after this here, and I will have v of e between parentheses. So here I have f gives e between parentheses dot, which does not have, the closure does not add anything to this item set. So that's my item set. So essentially I have built this DFA here, so whereby I'm starting here. If I successfully go over an E, I go to here. If I'm here and I successfully go over a plus, then I go here. If I successfully go over, for example, open parenthesis, then I go here, and so on and so forth. Okay. So then after you have this, well, keep in mind this was a long narrative here, but that's not the end of it. What you must do is then take this graph here, this DFA, and generate a table out of it, the parsing table with the action part and the go-to part. So how does this go? So you actually use these heuristics here, these 4 heuristics to integrate some entries inside of the table. You're going to have either go-to table entries that are going to be state numbers that you're going to put in the right part, the go-to part of the table. It's going to be states that you will add into these entries there. Then for the action table, you have either shift actions or reduce actions. And then eventually number 4 is actually a special case of a reduce action, which is the accept action, which is going to be only one of these. So number 4 is actually a special case of number 3 for the starting symbol, for the reducing of to the starting symbol. So how do we identify what are the targets for each of these heuristics? So essentially it goes, applies this heuristics for each of the states. So you try to find this pattern here that applies in each of the item sets of each of your states. So for the go-to table entries, you go in each of the states, you try to find in the item set of each of the state, you try to find elements or items in the item set of this kind, where the dot is in the middle here, So it's not a finished item. Okay, so that is not an item like this. That is not a completed item and has a non-terminal symbol after the dot. So it must be a non-terminal. It's a non-completed item that has a non-terminal after the dot. Then if you find one of these, then you put state of V alpha beta in column B. Essentially, after you go past this non-terminal, you will have V of alpha beta. And that's what you put inside of column B of the go-to table. So let's try to find them. Maybe we're going to find them here. So here, state 0. State 0, you have E here after the dot. So in state 0, you have E after the dot. So that's essentially V of E. What is V of E? It's state 1. So essentially, you're in state 0, go to table, state 0, E, state number 1. Then you go to all the other states. So let's go in the list here. That's going to be less confusing. So state 0, you encounter an E, you go to state 1. So in the go-to table under E in state 0, you'll see 1. In the go-to table under T, you'll see 2. On the go-to table under F, you will see 3. So 1, 2, 3, ETF in state 0. So state 0, ETF, 1, 2, 3. Okay. So you see that the go-to table is kind of sparse here. So you will not find so many of these. So that is, these are essentially those that you created a transition, the transition being a terminal symbol, okay, non-terminal symbol. Now let's say, okay, so that's it for state number 0. State number 1, we're looking for the dot, and there's a non-terminal symbol after the dot. There's no such thing in state number 1. State number 2, there's no such thing. There's no non-terminal after the dot. State number 3, either. State number 4, you have E after the dot, or T or F. So under E, state 8. Under T, state 2. Under F, state 3. State 4, ETF, 823. Okay. State number 5, there's no non-terminal after the dot. State number 6, there's T leads to 9, and then F leads to 3. So 6, state 6, under T, 9, under F, 3. And then state number 7, F, 10. So there's only one item that has a non-terminal symbol after the dot. It's this one here, F, so state 7, F, 10. State 7, F, 10. Okay, so that's it for the go-to table. Then let's go to the shift actions in the action table. So here what we're looking, again, is a non-completed item. But here it's non-completed item would have a terminal symbol after the dot. Keep in mind the shift action is somehow reminiscent of what we used to call the match in the Lr parsing. You're going over a terminal symbol. Okay, that's what the shift actions are. So for each of these items, which are not completed items and have a terminal symbol after the dot, you will add shift to the state V of alpha beta in the action table onto the state, from this state. So again, here, So we basically go over all the states, all the item sets of all the states. The pattern we're trying to find is non-completed items that have a terminal symbol after the dot. So here from state 0, open parenthesis, state 4. So that's shift 4, state 0, open parenthesis, shift 4. State 0, open parenthesis, shift 4. Then here, this one, state 0, ID, shift 5. State 0, ID, shift 5. Okay, I'm not going to go back and forth like this for all of them. I'm just going to identify them and say them. So here I have plus after the dot. So state 1 plus shift 6. State 2 times shift or star state 7. State 3, there's no such thing as any item that has terminal symbol after the dot. State 4, open parenthesis, shift 4. State 4, ID, shift 5. So state 4, open parenthesis, shift 4, and ID, shift 5. State 5, no such thing here. State 6, open parenthesis, shift 4. State 6, ID, shift 5. State 7, open parenthesis, shift 4. State 7, ID, shift 5. State 8 plus shift 6. State 9 times shift 7. And that's it. You see, it's pretty easy once you figure out how it works. It's not I say it's not rocket science to apply this. Of course, it's kind of a rocket science to figure out how to invent an algorithm like this. Okay, but applying it, it's not that complicated once you know how it works. Okay, so for the reduce actions, so how is it? So we're looking for completed items. So you see, that's the first time, the only place we're looking for completed items. Makes sense, because reduce action is about having identified a handle, which is a completed item. And what you want to do is to apply a reduce operation after having identified a full right-hand side, and you want to replace it by its corresponding left-hand side. So reduce actions, you're looking for completed items. And then what you're going to do is you're going to use the follow set. So this is our friend, the follow set here that comes back to us here. So you see that you need to have first and follow sets for any kind of parser, at least for LL and LR parsing. So you might say, well, that you don't need the first set. However, of course, if you remember, you need the first sets in order to compute the follow sets. But the first set specifically is not used in the processing of these heuristics. So I'm looking for completed items, and then I'm going to add inside of the action table, reduce actions that correspond to this particular application, the inverse application of this rule here. So in this case, I have actually numbered my rules. So for example, if I see R6, it's actually reduced using this rule. R2 is reduced using this rule. Okay. So I'm using, let's find this. Let's find the occurrences of this pattern. Here, do I have completed items? No. Here, I have completed item. Herever, it is the completed item of the starting, the rule that defines the starting symbol. So that's going to be my heuristic number 4. Okay. Now here, I have a completed item So essentially what I do here is I'm going to use follow of A in order to determine follow of the left-hand side, in order to determine under which column I'm going to introduce a reduce action that's going to use this rule here. So here, follow of E is plus close parenthesis $sign. I'm going to go into the action table under plus close parenthesis $sign. I'm going to use reduce E plus T. Reduce E plus T is 2, so reduce 2 here. Reduce 2 under plus close parenthesis $sign. Reduce 2. And I'm continuing down the list of my states. Here, T gives F dot. So state 3, and under follow of T is plus times close parenthesis $sign. Reduce T gives F. T gives F is my rule number 4. So in the states here, number 3 under plus $sign, close parenthesis $sign, reduce 4. Then I go here to my state number 4. Yes. This one does not have completed items. State number 5 has state number 5 has a finished item here. So under follow of F, follow of F is plus star close parenthesis $sign. I am going to put reduce using this rule here, which is I believe rule number 6. So rule number 6 here in state 5 under plus star close parenthesis $sign, reduce using rule number 6. And this state number 6 here does not have completed items. So this heuristic does not apply. Neither has state number 7. Neither has state number 8. State number 9 has a completed item. So follow of E is plus close parenthesis $sign. I'm going to put reduce using this rule under state 9. State 9 on what was my rule? Forgot. E gives E plus T. E gives E plus T is rule number 1 under follow of E, which is plus close parenthesis $sign, reduce using rule number 1 in state 9. Then the final, no, not the final one, this one here, a completed item. Follow of F is plus star close parenthesis $sign. T gives T times F is 3. So reduce 3, state 10 under plus star close parenthesis $sign. Then state 11 here, completed item, follow of F is plus star close parenthesis $sign. I'm gonna reduce using the parentheses rule, rule number 5, in state 10 under plus star close parenthesis $sign, reduce 5. And the last but not least, probably you might say the most important, the accept action. So there you're trying to find a completed item that actually is the completed item of the rule that defines the starting symbol. So which one it is? Completed item with an S as the left-hand side. This one here. So state number one, $, is accept. State number one, $, accept. Okay. This is how you construct this table. And then retroactively, this is how you actually build, you actually do the parsing process for Lr parsers. Now, this is, now hats off to Donald Knuth to have invented this. So you see there's kind of a lot of gymnastics only to explain how it works. I can't imagine what it is to actually invent it from scratch as it is not existing. It's kind of like when you have your favorite music, you listen to the music, and you're like, how the hell do you read such a beautiful song? Well, that's kind of what's happened to people to design wonderful algorithms. You need a lot of inspiration, and in this case, a lot of very meticulous thinking. Okay. So hats off to Donald Knuth to have invented that. This was a presentation about the SLR method. As I've hinted at before, the SLR method is the most simple. Not that the other CLR and LALR are way much complex. This is roughly the same thing, except that there are more some discriminants that are being used in inside of the generation of the item sets, so that it will somehow avoid some conflicts, either shift reduce conflicts or reduce conflicts. So we're going to see that in the next video. Thank you. Bye-bye.